This is section 14.4, part B. So we've introduced the idea of Green's theorem to find a circulation integral, and we'll practice that a little bit in example 2. It says using any method that applies, find the circulation on the unit circle. Now the first thing I'm going to notice is that defines my path C, and that is a closed path. Therefore, Green's theorem is going to apply all the time. We saw that it was a fairly simple process, so probably we'll just want to go ahead and, even though it says any method, probably Green's theorem is going to give us our most efficient method for these problems. We'll use that same path, that unit circle, and even though I didn't say so, like I told you guys, we'll assume the counterclockwise orientation. And we'll do it 3 times, once for each of these vector fields. So in A, we'd like to find the circulation for the radial field. Remember what the radial field looks like, right? All the vectors are going out from the origin. Before I even start doing this problem, I'm going to think about the fact that if I've got a vector coming out from the origin, it doesn't push my object along that circular path at all. Doesn't help it, doesn't hurt it, just doesn't do anything. So I'm kind of expecting a circulation of 0. Let's see what we get. So using Green's theorem, our circulation integral is going to be the double integral over the region of g sub x minus f sub y. And in this particular case, let's see, here's f and g. G with respect to x is 0, and f with respect to y is also 0. So I don't really even have to set up that integral, because no matter what, when I integrate 0, I'm going to get 0. So like we predicted, 0 for a circulation there. By the way, notice what happened here? This is the curl. And since the curl is 0, f is what we were calling conservative, and our new word irrotational. So I did have a conservative vector field, or an irrotational vector field, on the closed path, which was one of those conditions for the FTC to give me 0 as well. So we can kind of see all these pieces starting to come together. All right, for part B, this time we've got the rotational field, minus yx. And again, we've seen that one a few times. If you can kind of visualize that in your head, all of the vectors do push in that sort of a circular pattern around that circle, so I would expect to get a positive circulation. The rotational field definitely helps me as I move around this path. All right, so let's see. We've got a new f and g here. So g sub x is 1 minus f sub y would be negative 1. So I actually end up with the double integral of just the constant 2. Now I'm going to notice that since the circle is my region R, right? R is just the interior of my path, so there's R. It probably would be easier to set this up in polar coordinates. Circles are really nice in polar coordinates. So I think I'm going to use for my dA the polar form, r dr d theta. And this is a unit circle, so my radius would go from 0 to 1. And I want to go all the way around from 0 to 2 pi. 2 pi, I can just bring that down. Theta doesn't appear anywhere else except the d theta. And then the integral of 2r dr would be r squared from 0 to 1. So I'm just going to get 2 pi times 1 minus 0, or 2 pi. So yes, a positive circulation. The rotational field definitely does help me move around that circle. In fact, it helps me perfectly. All right, the last one. We've got the vertical field, 0x squared. There's no horizontal component to any of the vectors. The vectors are perfectly vertical. And because the x is squared, it's always going to be a positive vertical component. So my vector field is going to go up all the time. I think what's going to happen here is that when I'm trying to move up over here, that vector field is going to help me. But when I'm trying to move down over here, that vector field is going to move against me. So whatever helps me here is going to hinder me on that side, meaning it's likely that the net effect on the circulation should be 0. Let's see if we can get that mathematically. All right, so again, a new f and g. G sub x will be 2x minus the f sub y, which will be 0. And the limits of integration are so nice in polar coordinates. I think I'll go back to polar again. 2x, I'll write that as 2r cos theta. And the dA will be r dr d theta. And that way I can just say my circle goes from 0 to 1 in radius and 0 to pi for the 2 pi rather for the angle. Unfortunately, I can't use my theta trick this time. I do have a cosine theta in the integral, so I'm going to have to keep that. In fact, let me write this out one more time. I can pull the 2 out front if I want to, and that's going to be an r squared cos theta dr d theta. Integrating the r squared with respect to r is going to give me 1/3 r cubed. I'm going to actually put the 1/3 out here. Cos theta, going from r equals 0 to r equals 1. And let's see, that would be 1 cubed, or just 1 cosine theta, minus 0 cosine theta. And you can do that one either by hand or on the calculator. Either way, you're going to come up with 0. So as expected, not that we don't get help or lack of help or hindrance from the vector field, it's just that they basically cancel one another out. What helps me on one side works against me on the other. All right, so there's Green's theorem for circulation integrals. On the next page, we're going to take a look at doing Green's theorem for flux integrals. So here's the flux integral form of Green's theorem. Our flux, f dot n ds, over a closed path, notice that little circle again, indicating the closed curve C, and again, this really is for traversed counterclockwise, can be found by taking the double integral over the region R of the derivative of f with respect to x plus the derivative of g with respect to y, dA. So, a few things. First of all, similar idea here. What we're saying is, if we've got some closed curve C, and we're orienting it counterclockwise, then the flux across the boundary, remember the flux is kind of what's going across that boundary, so the flux across C is determined by something that's happening inside the region. Okay, talk a little bit about what that something is again. But again, ultimately, the flux across the boundary, something that's happening on the boundary, gets determined by something that's happening inside the region R. All right, in order to talk about what that something is, let's look at what we're integrating over the region R. This f sub x plus g sub y. This thing, again, we give it a name. This is called the two-dimensional divergence of f. And again, we'll discuss the whole idea of divergence along with curl a bit more in the next section. But for now, essentially, if we call that the divergence, then we'll sometimes see this version of Green's theorem written as, and I can put my little circle here, the flux, the integral of f dot n ds, is the double integral of this, the divergence of f dA. Again, we'll come back to exactly why those things maybe make a little bit of sense when we talk more about what exactly we interpret divergence and curl to mean in section 6. All right, second little note. If this divergence, f sub x plus g sub y equals 0, then all of the following are true. First of all, that means that you've got 0 in the integral. So the flux integral is just going to give you 0 on our closed curve C. Secondly, since we've now defined this to be the divergence, we can write that the divergence of f is 0. And thirdly, if I rewrite this, just moving the g sub y to the other side, f sub x equals minus g sub y. If you look back, that's actually the condition for a source-free vector field. So f is source-free. All right, let's look at an example of calculating flux using Green's theorem. So in example 3, I've given us this vector field f, x squared comma 2y squared, and I'd like to find the flux on this curve, which again I know it's not shown in your notes, so if you can sketch that in, just an ellipse, negative 3 to 3 on the x-axis, and negative 1 to 1 on the y-axis. And I'd like to once again do this twice. We'll do direct evaluation, or in other words, parameterization, and then we'll also do it using Green's theorem, and hopefully see that we can come up with the same result either way. All right, so method 1, let's parameterize. Parameterization here, since we're going counterclockwise, we'll use cosine for the x, and that will be a 3 cosine t. And then sine for the y, just 1 sine t. That means our prime is going to be negative 3 sine t, comma cosine t. And I guess I didn't mention, we are going all the way around, so t will go from 0 to 2 pi. All right. Because we're doing flux this time, we also need n. And remember, to get n, we swap these, so the cosine t becomes the first coordinate. And then we change the sign when we bring this one over, so positive 3 sine t becomes the second. Finally, I need f. So using my x and y from the original definition of r here, f is x squared, so 9 cosine squared t, comma 2y squared, so 2 sine squared t. All right, our flux, integral from 0 to 2 pi of f dot n which is going to give me 10 cosine cubed, or no, 9 cosine cubed t, sorry, plus 6 sine cubed t. And that's an excellent time to use the calculator. I did that, and I actually got 0 for the value of that integral. If we think about this one for a minute, we can probably see why. Actually, I got to thinking maybe we should really look at the actual graph here. What you're seeing is the graph of the field plot in Maple, the vector field. And if you'll notice, all of the vectors are going up and to the right. That's because the vector field was x squared comma 2y squared, so x and y are always positive. And then I've graphed the ellipse on top of that. If you're curious and wanted to know how that was done, I'll show you my code here. Let's see. I think I can. All I did was I went ahead and assigned E to an implicit plot. That's the equation for the ellipse. And then a little bit higher up, I had created the vector field up here. You'll notice that's just my, oops, a little bit higher there. That's just my field plot. There we go. So there's my field plot, and I had assigned that to the variable f. So f is the field plot. There's the vector field x squared plus 2y squared. And then E was the ellipse. And then I just had Maple display them both. So let me just get back down to that display. There we go. So I said display E and F, and there we are. At any rate, what I'm looking for you to see is that we got a flux of 0 when we did the math here. And you'll notice that, yes, there are things that cross outward, right? From here, we're going out of the ellipse. From here, we're going out. So there definitely is stuff that crosses that boundary in the positive or outward direction. But there's also stuff on this side that comes in. That's going to create negative flux. And ultimately, if I just look, for example, at this quadrant, everything that comes in down here eventually goes out up here. And that's going to be true everywhere. So it's not that nothing ever crosses this boundary, it's just that what comes in is balanced by what goes out. All right, let me close down Maple here and go back to our notes. So, not surprisingly, we did get 0. Let's go ahead and redo this problem now using Green's theorem and see what happens there. So method 2, our new form of Green's theorem for the flux integrals. I'm just going to make a quick sketch of my ellipse again. There we go. And according to Green's theorem, we can calculate the flux by taking the double integral over the region R, which is now the interior of our ellipse, and we need to take f sub x plus g sub y. That divergence is our integrand. Just a reminder, f was x squared comma 2y squared. So that provides my little f and my little g. So f sub x is 2x, and g sub y would be 4y. Because this is an ellipse, not a circle, I don't think polar coordinates would help me very much. So I'm going to stick with rectangular, and I'm going to go with, actually I think I'm going to go dx dy here. I'll show you why in just a minute. I need the equation of this ellipse. It would be x squared divided by 3 squared, or 9, plus y squared over 1 squared, or 1, equals 1. And if I clear my fractions by multiplying through by 9, I have x squared plus 9y squared equals 9. And that's actually why I decided to do dx first. I'm going to solve for x just to avoid fractions. X squared would be 9 minus 9y squared. And that's going to give me x's plus or minus the square root of that. So when I think about my vertical, oops, I just said I was going to do x first and I went and drew a vertical rectangle. That wasn't right. Ignore that vertical rectangle. If we're doing x first, we have to do a horizontal rectangle. And the x on the left side would be the negative square root. And the x on the right side would be the positive square root. So that's going to provide me with my x limits of integration. And then the y limits of integration would go from down here at -1 to up here at +1. All right, so let's see what we get. Integrating with respect to x is going to give me x squared plus 4y times x. And x goes from the negative square root to the positive square root. And let's see, x squared is going to give me 9 minus 9y squared plus 4y times that square root of 9 minus 9y squared. I subtract, plugging in the negative square root. When I square it, the negative goes away, so I'll just have 9 minus 9y squared again. And then because of the negative, I'll end up with a minus 4y times the radical. And that's a dy. All right. Seeing as I am subtracting, 9 minus 9 is going to be 0. That'll be a negative 9y squared, and that'll become a positive 9y squared. And I end up with 4y times the radical minus a negative is another 4y times the radical. So I have 8y times that radical. And that's a good one for the calculator to do. I did plug that into my calculator, and I was able to get 0 again. All right, I wouldn't argue with you if you said that Green's theorem might not have actually been the fastest way to do that one. It might have been a little bit easier to parameterize, but the whole point here was just simply to see why it's sometimes, the fact that we could get the same answer both ways. All right, I've got one last example, so we're going to forge ahead here in this video and finish up with example 4. All right, so using any method that applies, we'd like to find the flux on the unit circle for each of these vector fields. And notice this is the same one we just did the circulation for a little bit ago. So once again, I'm on the unit circle. It's closed, meaning it's okay to use Green's theorem. Remember, one thing that we have to be really careful with Green's theorem, it's a great, powerful tool, but unless we've got a closed curve, we cannot use it. So make sure you're only using it if you do have Green's theorem. Or excuse me, if you do have a closed curve. All right, so our unit circle does provide us with that closed curve. We're in good shape. We'll assume the counterclockwise orientation since I once again neglected to tell you. All right, keeping in mind we want flux, the radial field, xy, is going to provide vectors that always go out from the origin. So I do see an outward flux. It's going to cross that boundary in the outward direction all over the place. I'm expecting a positive value here. So let's see. Green's theorem says take the double integral over the region. So we'll now look at the region R, which is enclosed by our path. And remember that it is f sub x plus g sub y dA for flux. But that's what changes depending on whether it's circulation or flux. I'm doing flux now. So for the radial field, f sub x is 1, g sub y is also 1. So just got a nice constant that I'm integrating, constant 2. And since I've got a circular region, I think I'll use polar coordinates, so dA will do as r, dr, d theta. My radius from 0 to 1, and the angle going all the way around from 0 to 2 pi. D theta is the only mention of theta, so I can pull down that 2 pi for the first integral. And then this is really just the integral of 2r, which gives me r squared from 0 to 1. And that's going to give me 2 pi. So as expected, a positive flux across the boundary from the vector field that just is the radial field going out in all directions. All right, what about B? This is the rotational field, minus yx. Remember here, the vectors are going to rotate, they're going to go around right along tangent to that circle. They never actually cross the circle, they just stay tangent to it all the way around. So I'm not expecting to get, I'm actually expecting to get a zero flux. The vector field does not cross that boundary at all. Let's see if it happens. Got my F and my G. So using Green's theorem, F sub x is going to be 0 this time, plus G sub y is also 0, meaning I don't really have to do anything else. I already know with an integrand of 0, I am going to get 0 for my flux. All right, finally in C, we want to go with the vertical field. F is 0x squared. On that one, this is all vectors that are vertical pointing upward, since that's always a positive value in the y. So everything that enters down here is going to exit again up there. So I would expect this time to get a 0 again, not because nothing ever crosses the boundary, but because I have a negative flux when it enters and a positive flux when it leaves. Let's see if we get 0 again. So once again, F sub x is going to be 0. G sub y, also 0. And there's our 0 already. All right, so that's Green's theorem. 2 forms, circulation form and flux form. Just make sure you're using the right form depending on which line integral you're trying to find. And that brings us to the end of 14.4.